Let's talk about a process that's sort of similar to fermentation in our bodies, but in the plant. Now, some plants that live in hotter environments, they run the risk of dehydration all the time. Every time they open a stomata, they can lose water. And so as a consequence, they try to keep their stomata closed as much as possible. Now, if your stomata is closed, and we didn't draw this in our original diagram, but where is the CO2 coming from? It's coming from the air, right? And it's coming through the stomata. Now, if your stomata are closed, we have no way of getting CO2. And not only that, the sun is still shining, so we're making oxygen. So the oxygen begins to build up in the cell and the CO2 decreases. So if that becomes the case, our oxygen starts building up, our CO2 is getting low. Rubisco, and this is one of those weird evolutionary relics, Rubisco can't tell the difference between carbon dioxide and oxygen. So as a consequence of that, Rubisco will grab oxygen and put that into the cycle instead of CO2. Now when that occurs, can we make G3P? Well, of course not. There's no carbon going into the cycle, and so it's a waste of the cycle. The ATP gets used, the NADPH gets used, but nothing gets built. And that is called photorespiration. And that's bad for the plant. It will kill the plant eventually. And so there are two modifications through evolution that plants have made, those that live in high heat, low moisture environments. And I'm going to show you both of those, but I got to erase this, so just a moment. Okay, so we're just erasing enough of this so that we can draw this process. The two ways that we can get around photorespiration, one of them, I'll draw right here, and the second one right here. Okay, so this is the Calvin cycle going on. Okay, so our little Rubisco enzyme, we'll just call him Rube, is right here. Now, one way we can prevent Rubisco from using oxygen instead of CO2 is to completely separate it from the process of grabbing CO2. And so in these plants, CO2 is grabbed by a different enzyme, a newly evolved enzyme, and put into 4 carbon sugars. And then, one at a time, these CO2s are broken off and given to Rubisco. So at nighttime, or whenever it's cool, where they can gather CO2 and keep their stomata open, they will build as much of these 4 carbon sugars as possible. And then anytime Rubisco needs one, they just feed it to it. It's the equivalent of putting Rubisco in a playpen and then throwing Cheerios at it when it's hungry. Okay, and so these types of plants are called C4 plants. So the regular photosynthesis is C3. Just put that in parentheses. So these are C4 plants. They build these 4 carbon sugars. The other way to do it is to separate it by time. And so in this case, when it's dark out, when it's nighttime versus daytime, when it's nighttime and the stomata are open, this plant will bring in as much CO2 as possible and store them as all different kinds of carbon molecules, usually 4s. Okay, and then it will shut its stomata during the day and shut this process down. And then during the day, it will allow the Calvin cycle to run with these gathered CO2s. So the only difference is this is an actual physical separation between the two processes, and this is a temporal or time separation between the two. So these are called CAM plants, and it stands for crucillation acid metabolism. You don't need to know that, just call them CAM. So types of plants that do this, so the C4 plants, corn, sugar, and a lot of grasses are C4. And CAM plants are cacti, succulents. and both of them have evolved ways of living in the heat by separating the process of carbon fixation and the Calvin cycle.